This video is part of Electrify Everything, a very short course. In this episode, we ask, how wasteful is our energy use today? To start, let's go back to the 1700s, when steam engines like this one helped kickstart the Industrial Revolution. It was first patented by this guy, James Watt, in 1765, and while it was much better at using energy than the engines that had come before it, it used only around 10% of the energy for useful motion. And we say that this was 10% efficient. Yet, this was still a big improvement over earlier engines. So why did it waste the other 90% of the energy? Well, Watt's engine is a little complicated, but modern engines work on the same principles, whether it's car engines, train engines, and even most power plants. So let's look at this much simpler toy engine instead. It's known as a Stirling engine for its inventor, Robert Stirling. And the way it works is you put a glass of hot water at the bottom, then you put the toy engine on top, and the engine has a sealed air chamber that sits directly above the hot water. And there are also two pistons that can move up and down, along with a flywheel on top that help keeps things moving. Alright, so here's a video of the engine running, taken with a regular camera on the left and with a special thermal camera on the right. It's really not obvious how it works, is it? Let's just watch it for a couple seconds. Alright, and here's the engine in slow motion. I'm going to explain how it's working, but don't worry if it's still confusing. Alright, here's a page from the great website called Animated Engines, and let's name the little piston on top the power piston, and its job is to give the flywheel a push to keep it going. And we'll name the big piston on the bottom the displacer piston, and its job is to move the air back and forth between the bottom and top of the sealed air chamber. Now, the way the engine works is that the hot water heats the air, and that causes the air to expand, and then it pushes the power piston up, which is what gives the flywheel a little push. The displacer piston then moves the air to the top, where it cools down, and since the cooling air contracts, the power piston moves down, and then the displacer moves the air back down, and the cycle repeats. So, if we bring back the motion, you can see the up, down of the pistons. But really, the key is having a warm side where the air heats up and a cool side where the air cools down. And it's clear with the thermal image that there's a warm side and a cool side. But think about it. If we just left the glass of warm water out with no engine on top of it, what would happen? Well, the water would just cool down to room temperature by itself. But when we stick an engine in the way, we can extract some useful motion. To explore this further, let's use a water wheel analogy, which is what this young engineer named Sadi Carnot did in the early 1800s. Now back then, people were using water wheels to power lots of stuff by sticking them into water that was flowing from higher to lower height already. So the bigger the height difference, the more the wheel can power. Think of what a big waterfall could power versus a small river. And as it spins, the water can extract some useful output from the falling water. But the water also has to flow out at a lower height, and if it doesn't flow out, it will back up and overflow the water wheel. So imagine building a dam after the water wheel, and then the water would pool up and eventually flood the wheel, and it would stop spinning. Carnot used this analogy to picture heat flowing into an engine at a higher temperature, and the bigger the temperature difference, the more the engine can power. And as it runs, the heat engine can extract some useful output from the heat, but the heat also has to flow out at a lower temperature, and if it doesn't flow out, the engine will overheat. So just like we can think of a waterfall powering the water wheel, we can think of a heat fall powering the heat engine. And this heat fall idea applies to all heat engines, whether they run cars, trains, or power plants. Alright, so back to our Stirling engine. Let's say there's 100 units of heat energy coming from the hot water into the engine. One estimate for this toy is that only 1 unit of that energy is going towards the useful motion, and the other 99 units are going out with the cooling, and we call this waste energy, and some always has to flow out or the engine will overheat. And we say this toy engine is 1% efficient, again meaning it makes use of only 1% of the energy input, and it wastes the other 99%. Now that's pretty low, but it's only a toy. So if we now look at something like a gasoline-powered vehicle, the left side represents the energy source, with gasoline providing 100% of the original fuel's energy. And the right side represents where the energy is used by the car. And you can see around 70% is going straight to engine losses. So that's the heat outflow of the engine cooling down. And you can feel it in part in the hot exhaust if you walk behind a gasoline car. So if we go back to our red arrows, this one represents the 100 units of energy from the gasoline. This one represents the wasted energy. And this one is the actual motion of the car. And it uses only 21% of the gasoline's energy to move the car. That's pretty low. But if instead we look at an electric vehicle, there are still losses to charging and other things, which are outlined in red. But the energy can also be recaptured by brakes and fed back to the battery, which greatly reduces the waste. And of the 100 units of electricity used to charge the car, only 11 units are wasted, and the other 89 units are used to move the car, which makes it a much improved 89% efficient. So, for the same 100 units of input energy, the electric vehicle can move 4 times as much as the gasoline-powered vehicle. Or if instead we make them both output 21 units of motion, the EV only needs a quarter of the input energy as the gasoline car, which is amazing. These kinds of diagrams, they're called Sankey diagrams after this guy, Captain Sankey, who invented them in the early 1900s. And his first diagram was meant to illustrate the efficiency of steam engines. And I'll make it clearer by adding the arrows for the input, the waste, and the useful output energy from the steam engine. And now we're ready to look at this Sankey diagram, which shows the energy used in the United States in 2021. Now it looks confusing, but it's actually easier to read than it seems. You just have to know on the left are the energy sources, and the widths of the lines represent how much energy comes from each source. On the right are the energy uses in pink. The dark gray lines that come out of those represent the useful energy that we want, which is labeled energy services on the diagram. And the light gray lines represent the waste energy, which is labeled as rejected energy. Also note that electricity generation is in the middle, and we'll deal with that separately in the video, Where Does Electricity Come From? For now, let's just look at transportation and notice that almost all the energy flowing in from the left is from petroleum, and that's where gasoline comes from. And there's a tiny little orange line that's coming down from electricity. So if we isolate transportation, we can add our red arrows and say that for 100 units of energy input, we get 21 units of useful motion. I gotta get out of the way here. Here we go. And 79 units of waste energy, which is 21% efficient. That's pretty wasteful. But if we electrify our transportation and we use as a proxy the 89% efficiency of electric vehicles, we'd only need a quarter of the energy input. And this is one example of why we say that electrification is the efficiency. So for transportation, when we electrify our wasteful gasoline cars and our diesel school buses, we'll use a lot less energy to get the same useful motion that we want. And we'll do it without any of the emissions if we power it with renewable energy. All right, so to summarize, heat engines are incredibly wasteful because we heat them up with fossil fuels. We must cool them down or they'll overheat. Most of the energy input is wasted through cooling, and burning fossil fuels creates air pollution, especially carbon dioxide, which is causing climate change. Okay, if you've got any questions, comments, feedback, email us, schools@rewiringamerica.org.